Okay, I'm going through part 2 of problem 2 from the divergence theorem. I'm going to hope I can get through this without making any big blunders. So remember in the last video I sort of laid down the foundation for this, and I said that we need to break this into, if we're going to do this without the divergence theorem, we're going to end up with 3 different surface integrals. I'm going to start with the bottom one. So to solve the bottom one, I'm going to use the formula number 2 that gives me this form, the function, and I know the function is dot product with the normal vector for the surface, ds. And in this particular case, I'm starting at the bottom. I know that the normal vector at every point is minus k. This is a circle sitting in the xy plane, so the normal vector is minus k. So now I'll rewrite this. It's a surface integral. I don't have any bounds on this yet, but you'll see I'm not going to need to worry about this. And it's going to be 2x minus 2y z squared dot product with the normal vector for this, which is 0, 0 minus k ds. Well, look at when I take the dot product here, I end up getting 0 plus 0 minus z squared ds. But I'm sitting in the xy plane here, and z is equal to 0. So this is equal to the integral of 0. And it doesn't really matter what area I'm integrating this over. In fact, I'm integrating over a circle with a radius of 2, but this is going to be equal to 0. So I'm done with my first surface integral. This function integrated over the bottom surface is equal to 0. Now let me do the second one, and the second one is going to be the top one. And the reason I want to do that next is it's really pretty much identical. So I'm going to take f, and I'm going to cross it with the normal vector. Now in this case, the normal vectors are pointing straight up. They're positive k. So I could rewrite this as the surface 2x minus 2y z squared dot product, this time with 0, 0, 1k ds, and this is equal to z squared ds. Now I'm on the top now. I'm at the top of the surface, so this is equivalent to writing it as h squared ds. And so I'm integrating something over an area, and I know what this area is. It's a circle. It's the top with a radius of 2. So this integral is equal to 4 pi h squared. So notice here's the function. I'm integrating over something. I'm integrating over this area. I could just say it's equal to that now. So now let me keep a running total. I found for the bottom the surface integral is 0. For the top it's h squared over the circle. That gives me 4 pi h squared. And now let me move to the third integral, which is going to be this third surface integral, which is going to be the side. And that's a little bit more difficult. So I've got this side here, and I'm going to rewrite it as a vector valued function in u and v, in other words in parametric form, and I'll say that RUV is equal to 2 times the cosine of u. I've got a radius of 2 here. 2 times the sine of u, where u is the angle, and then v is going to be the height. So there's my vector valued function there that describes this cylinder. Think about that. If you take this and you square it, you'll end up with an equation that gives you that x squared plus y squared is equal to 4. I'm going to use this integral RUV. This will be my xy value is written in u and v, dot product with RU cross RV du dr in some order, du dv in some order. Okay, so before I do anything else, let me find out what RU is. Well, that's going to be equal to negative 2 sine u 2 cosine u 0, and what RV is, well, here's my V, so that's going to be equal to 0, 0, 1, and when I take the cross of RU crossed with RV, and you know how to do this, you'll end up with um, let me double check. You end up with 2 cosine U I plus 2 sine U J plus 0K. So you could check this on your own, set up your matrix, and you'll find that that's what it should be. So now I'm ready to plug everything in, and I'm interested in the function rewritten in terms of u and v, the vector value of the function, times r dot product with r u cross rv dA. So, well, let's see. When I rewrite this function, this is my x and y, it's going to be 2x, but x is 2 cosine u, 2y, but y is 2 sine u, 0, dot product with ru cross rv, which we just said was, I'm going to have to write this down here, sorry, 2 cosine u I plus 2 sine u j plus, sorry, 0, plus 0k. And when I take that dot product, I end up with 8 cosine squared u minus 8 sine squared u du, and my r goes du dv, my v goes from 0 to h, and my u goes from 0 to 2 pi. Now before I do anything else, I'll pull out the 8 and I get cosine squared u minus sine squared u, and you may not remember this trig identity. It's a good thing to remember. This is equal to sine u cosine u. Yes, that's right. And now, so now when I go, I'll take that 0 to h sine u cosine u from 0 to 2 pi dv. When I plug these in, I'm going to get 0 again, so it's 8 times 0, h0 dv. Well, this again is going to be equal to 0. So now let me add to my running total. 0 plus 4h squared pi plus 0 is equal to 4h squared pi, and that should be the total surface integral of this. Now let's see if I got to get to my class, but let me see if I can real quickly do the divergence for this. So the function is equal to the divergence of the function. So my function was 2x minus 2y z squared, I think. So the divergence of that is going to be equal to 2 minus 2 plus 2z or 2z. And now when I do a triple integral of this 2z, and where am I going to go? Well, my height is from 0 to h, so I'll do dh. I'm sorry, that'll be my dz. Then 0 to 2 is going to be my radius, and 0 to 2 pi is going to be my d theta. So I'm rewriting it in polar form. Let's see, my z goes from 0 to h, my radius goes from 0 to 2. I'll leave you, I have to run the class, I'll leave you to look at this. This is really the easiest part. When this is solved, you end up with 4 pi h squared, exactly the same thing you got when you did it by all those steps. Think about this. It took me 1, three different integrations and about 2 or 3 pages to do what I was able to do here with the divergence theorem in just 3 or 4 different lines. So see if you can understand what the divergence theorem does for you. In the end, what's weird is we've integrated over a volume to find the surface integral. But that's what we did.